Hi, here we meet again at the second part of Ethernet switching. For those who are new at this channel, please do not forget to subscribe. At the first part of Ethernet switching, we learned about Ethernet frames and Ethernet MAC addresses. And now we will continue at the MAC address table and switch speed and forwarding methods. Let's go and see each of them. After we learn about Ethernet MAC addresses, it is time to talk about how a switch uses these addresses to forward or discard frames to other devices on a network. If a switch just forwarded every frame it received out all ports, your network would be so congested that it would probably come to a complete halt. A layer 2 Ethernet switch uses layer 2 MAC addresses to make forwarding decisions. It is completely unaware of the data being carried in the data portion of the frame, such as an IPv4 packet, an ARP message, or an IPv6 neighbor discovery packet. The switch makes its forwarding decision based only at the layer 2 Ethernet MAC addresses. An Ethernet switch examines its MAC address table to make a forwarding decision for each frame. Unlikely the legacy Ethernet hubs, because the hub repeat bits out all ports except the incoming ports. As you can see in the figure, there is a switch with 4 ports, and the switch is just powered on. And the table shows that MAC address table in the switch has not learned the MAC address for the 4 attached PCs. You can see even that the MAC addresses are shortened for the demonstration. When you study about network, you may see that the MAC address table sometimes is referred to as a content addressable memory CAM table. Is the same, but we will continue using the term of MAC table. The switch dynamically builds the MAC address table by examining the source MAC address of the frame received on a port. The switch forwards frames by searching for a match between the destination MAC address in the frame and an entry in the MAC address table. For those, there are 2 steps that we can see, and the first step is learning. So the switch will examine the source MAC addresses, where every frame that enters a switch is checked for a new information to learn. It does this by examining the source MAC address of the frame and the port number where the frame entered the switch. If the source MAC address does not exist, it is added to the table along with the incoming port number. If the source MAC address does exist, the switch updates the refresh timer for the entry in the table. By default, most Ethernet switches keep an entry in the table for 5 minutes. If you will refer to the figure, you will see that the PCA is sending an Ethernet frame to PCD. The table shows the switch as the MAC address for the PCA to the MAC address table. You have to know that if the source MAC address does exist in the table but on a different port, the switch treats this as a new entry. The new entry is replaced using the same MAC address but with more current port numbers. The second process is forwarding. At the forwarding, the destination MAC address have to be checked if it is unicast, multicast, or broadcast MAC address. If the destination MAC address is a unicast address, the switch will look for a match between the destination MAC address of the frame and an entry in its MAC address table. If the destination MAC address is in the table, it will forward the frame out the specific port. If the destination MAC address is not in the table, the switch will forward the frame out all ports except the incoming port, and this is called as unknown unicast. By referring to the figure, the switch does not have the destination MAC address on its table for the PCD. So it will send the frame out all ports except the port 1. And if the destination MAC address is a broadcast or multicast, the frame is also floated out all ports except in incoming port. A switch receives frames from different devices, and it is able to populate its MAC address table by examining the source MAC address of every frame. When the MAC address table of the switch contains the destination MAC address, it is able to filter the frame and forward out a single port. By referring that, let's see how the switch will filter the frame. First, let's see that we have the PCD that is replying back to PCA. The switch sees the MAC address of the PCD in the incoming frame on port 4. The switch then puts the MAC address of PCD into the MAC address table associated with the port 4. And secondly, the switch, because it has the destination MAC address for the PCIe in the MAC address table, it will send the frame only out the port 1 as it is shown in the figure, because the switch has a MAC address entry for the destination. And then the PCA sends another frame to PCD as it is shown in the figure, but this time the MAC address table already contains the MAC address for PCA. Therefore, the 5-minute refresh time for that entry is reset. Next, because the switch table contains the destination MAC address for PCD2, it will send the frame only out port 4, as it is seen in the figure. We mentioned the switches uses their MAC address table to determine which port to use to forward frames, right? There are actually 2 frame forwarding methods, and there are good reasons to use one instead of other depending on the situation. Switches use 2 forwarding methods for switching data between network ports. The first one is store and forward switching, where this method receives the entire frame and computes the cycle redundancy check. We know that the cycle redundancy check uses a mathematical formula based on the number of bits 1 in the frame to determine whether the received frame has an error or not. If the cycle redundancy check is valid, the switch looks up the destination address and then determines the outgoing interface. Then the frame is forwarded out of the correct port. At the other method, this cut-through switching, and in this case, the frame forwarding method forwards the frame before it is entirely received. At a minimum, the destination address for the frame must be read before the frame can be forwarded. A big advantage of store and forward switching is that it determines if a frame has error before propagating the frame. When an error is detected in a frame, the switch discards the frame. Discarding frames with errors reduce the amount of bandwidth consumed by corrupt data. Store and forward switching is required for quality of service analysis on convergent network where frame classification for traffic prioritization is necessary. For example, voice over IP data stream need to have priority over web browsing traffic, and that's why in this case we use the method store and forward switching. If we will see the animation, it is demonstrated the store and forward process. As you can see, the switch will check for a match at the cycle redundancy check. If there is a match, then the switch will find the port for the destination MAC address to forward this frame. At the cut-through switching method, the switch acts upon the data as soon as it is received, even the transmission is not complete. The switch buffers just enough of the frame to read the destination MAC address so that it can determine to which port it should forward out the data. The destination MAC address is located in the first 6 bytes of the frame following the preamble. The switch looks up the destination MAC address in the switching table, determines the outgoing interface, and forwards the frame onto its destination through the destination switch port. The switch does not perform any error checking on the frame. And as you can see at the animation, it is demonstrated the cut-through switching process. There are two variants of cut-through switching. The first one is fast-forward switching, where it offers the lowest level of latency. Fast-forward switching immediately forwards a packet after reading the destination address. Because the fast-forward switching starts forwarding frame the entire packet has been received, there may be times when packets are relayed with errors. This occurs infrequently, and the destination network interface cards discard the faulty packets upon receipt. In fast-forward mode, latency is measured from the first bit received to the first bit transmitted. Fast-forward switching is a typical cut-through method of switching. The second method is fragment-free switching, and in this case, the switch stores the first 64 bytes of the frame before forwarding. Fragment-free switching can be viewed as a compromise between store and forward switching and fast-forward switching. The reason fragment-free switching stores only the first 64 bytes of the frame is that the most network errors and collision occurs during the first 64 bytes. Fragment-free switching tries to enhance fast-forward switching by performing a small error check on the first 64 bytes on the frame to ensure that a collision has not occurred before forwarding the frame. Fragment-free switching is a compromise between the high latency and high integrity of store and forward switching and the low latency and reduced integrity of fast forward switching. Some switches are configured to perform cut-through switching on a per-port basis until a user-defined error threshold is reached, and then they automatically change to store and forward. When the error rate falls below the threshold, the port automatically changes back to cut-through switching. An Ethernet switch may use a buffering technique to store frames before forwarding them. Buffering may also be used when the destination port is busy because of congestion. The switches store the frame until it can be transmitted. There are two methods of memory buffering as are listed in this table. The first one is port-based memory, where the characteristics about this buffering are frames are stored in queues that are linked to specific incoming and outgoing ports. A frame is transmitted to the outgoing port only when all the frames ahead in the queue have been successfully transmitted. It is possible for a single frame to delay the transmission of all the frames in memory because of a busy destination port, and this delay occurs even if the other frames could be transmitted to open destination port. And the other method is shared memory. In this case, the deposits all frames into a common memory buffer shared by all switches port, and the amount of buffer memory required by a port is dynamically allocated. The frames in the buffer are dynamically linked to the destination port, enabling a packet to be received on one port and then transmitted on other port without moving it to a different queue. Shared memory buffering also results in the ability to store larger frames with potentially fewer dropped frames. This is important with asymmetric switching, which allows all for different data rates on different ports, such as when connecting a server to a 10 gigabit per second switch port and a PC to 1 gigabit per second port. Two of the most basic settings on a switch are the bandwidth and the duplex setting for each individual switch port. It is critical that the duplex and the bandwidth setting match between the switch port and the connected device, such as computer or another switch. There are two types of duplex setting used for communication on an Ethernet network. There are the full duplex, where both ends of the connection can send and receive simultaneously, and the half duplex, where only one end of the connection can send at a time. Auto-negotiation is an optional function found on most Ethernet switches and network interface cards. It enables two devices to automatically negotiate the best speed and duplex capabilities. Full duplex is chosen if both devices have the capability along with their highest common bandwidth. And as you can see in the figure, the Ethernet network interface card for PCA can operate in full duplex or half duplex and in 10 megabits per second or 100 megabits per second. Duplex mismatch is one of the most common causes of performance issue on 10 and 100 megabit per second Ethernet links. It occurs when one port of the link operates at half duplex while the other port operates at full duplex, as it is shown in this figure. Duplex mismatch occurs when one or both ports on a link are reset, and the auto-negotiation process does not result in both link patterns having the same configuration. It also can occur when users reconfigure one side of a link and forget to reconfigure the other. Both sides of a link should have auto-negotiation on, or both sides should have it off. Best practice is to configure both Ethernet switch ports as full duplex. Connection between devices once required the use of either a crossover or straight-through cable. The type of cable required depending on the type of interconnecting devices. For example, in the figure, it identifies the correct cable type required to interconnect switch to switch, switch to router, switch to host, or router to host devices. A crossover cable is used when connecting like devices, and a straight-through cable is used for connecting unlike devices. Most switch devices now support the automatic medium-dependent interface crossover feature, Auto-MDIX. When enabled, the switch automatically detects the type of cable attached to the port and configures the interface accordingly. Therefore, you can use either a crossover or straight-through cable for connection to a copper 10, 100, 1000 port on the switch, regardless of the type of device on other end of the connection. The auto medium dependent interface crossover feature is enabled by default on switches, and however, this feature could be disabled. For this reason, you should always use the correct cable type and not rely on the Auto-MDIX feature. Auto-MDIX feature, so Automatic Medium Dependent Interface Crossover, can be re-enabled using the MDIX Auto Interface Configuration command. With MAC address table and switch speed and forwarding methods, we are ending all the materials about the Ethernet switching. See you to the next session, and please do not forget to subscribe at this channel for other videos.